Have you ever wondered how to find the volume of a donut? What we call in mathematics a torus? Probably not, but the solution can be reached in multiple interesting ways. First, in geometry, by borrowing the methods of simpler proofs and cutting a problem into bite-sized pieces. Or alternatively, in calculus, through a textbook application of integral calculus. In other words, the formula can be reached at two levels of certainty: an answer that looks visually correct, and one proved correct by equations. Let's begin with the geometric method, by first observing how Archimedes devised his famous proof for the area of a circle. By splitting a circle into a set number of slices, let's say n, and assigning them each into two groups, uppers and bottoms. Each slice can match together with another and be arranged into a shape that vaguely resembles a rectangle. As n then increases towards infinity, this correlation becomes clearer, until we have a rectangle with the height of the circle's radius and a base of half the circle's circumference. We know rectangles are easily measured by a formula: base times height equals area. So by using this area formula, the rectangle, which was derived from a circle, has an area of pi r squared. Archimedes had found that any circle's area is pi r squared by splitting up and rearranging his problem. Well, this is great, but how can we apply this knowledge to our problem? Before anything, we're going to have to label some key variables within a torus. This vertically oriented circle can be isolated, and we will mark down its radius as r. Likewise, this circle that sits in line with the center of the torus's revolution can be identified. It's a locus from the center of the solid. We will note this and mark its radius as a capital R. Now let's borrow from Archimedes' method, though this will be easier to visualize from a top-down perspective. Just don't forget that each slice is still in 3 dimensions. If we cut this shape into a set of n slices again, we can split them into two groups, uppers and bottoms, so they can be matched together and rearranged into a cylinder of sorts. Now, as n approaches infinity, watch how the created shape becomes more and more like a cylinder, until we have two solids with exactly equal volumes. Putting these back into 3 dimensions, we can once again match together equal parts. We know that this face of our cylinder corresponds to the revolving circle of the torus. Therefore, we can mark this face as pi r squared. So far, our application has been nearly identical to the proof of a circle's area. But what is the cylinder's height? In the proof for a circle, Archimedes identifies the base of his devised rectangle as half of the circle's circumference. But what is our equivalent here? It is the circumference of the horizontally oriented circle, and this appears intuitive enough, so the derived cylinder's height is 2 pi r. The formula for a cylinder's volume, like a rectangle's area, is simple. It's height times pi r squared. Therefore, our volume is pi r squared times 2 pi r. This should be the volume for a torus. However, this solution doesn't really feel concrete, and we're not finding the area of a simple 2D shape anymore, rather the volume of a curved solid. Can we really presume that a torus could be warped into a cylinder? Our solution feels optimistic, and this is not necessarily a reassuring feeling in maths. What if we fail to account for something, and how can we be sure? Let's leave the obscurity of visual geometric proofs and turn to something more absolute. We want a definitive solution after all. This can be done by the process of integral calculus. To begin, we will graph a circle using the function x squared plus y squared equals radius squared, and then elevate its center point to 0, r. To achieve this, we must change our function so that it's x squared plus y minus r squared equals radius squared. Notice that the function y equals r will pass straight through its center point, and its domain lies between negative and positive r. Our ultimate goal will be to rotate this function around the x-axis in order to create a torus. After that, we can integrate to find its volume. The first step towards this is to rearrange our function to be in terms of y. Move over the x squared, square root both sides, and finally isolate y. This yields a positive and negative answer, with each representing the upper and bottom half of the circle, divided by the function y equals r. Next, we will rename each of these functions upper x and bottom x. The positive function, when integrated, will provide this blue area, and the negative function will provide this red area. Therefore, the difference of ux and bx will yield the area of the initial function y. Keep this in mind. In order to find the volume of a function rotated around the x-axis, we use this formula, pi times the integral of y squared dx. We can then apply this formula to the difference of ux and bx, subbing in each function. Note that the domain has been used as the limits here. After this, the steps are as follows. Expand both sets of brackets, then apply the negative to this set of values so we can simplify further. Notice we have created some like terms, r squared and r squared minus x squared, that will cancel each other out. This results in a constant, 4r, which we can remove and place in front of the integral. To integrate further, we must make a substitution, so let x equals r sine theta. Therefore, the differential of x will be equal to r cosine theta d theta. We can now recognize where x and dx will substitute, and we can proceed. Later, we can come back to this equation, but first we need to alter our limits due to the substitution. As x equals r sine theta, recalling our limits negative r and r sine theta equals r, dividing both sides by r, sine theta equals 1, and then theta is arcsine 1, simplified to pi on 2. Therefore, our limit of r has become pi on 2, and the negative limit can also be said to make this change. With our new limits, we can continue solving the integral. Let's first change our newly discovered limits, and continue by expanding this term into r squared times sine squared theta. Noticing that each term has a common factor of r squared, we will then factor it out as such. This square root can be distributed across both terms, so that we can simplify further. However, before this, we will substitute 1 minus sine squared theta for cosine squared theta, because of this trigonometric identity. Now notice that we have two terms, r and cosine theta, both squared under square root signs. These signs will cancel out, and we can once again simplify to r squared cosine squared theta. The constant r squared can then be removed to be in front of the integral. Next, we will substitute cosine squared theta for half 1 plus cosine 2 theta, as another identity allows this. The half is a constant that we can remove against the 4, resulting in 2. Finally, we can integrate into theta plus half sine 2 theta, and substitute our limits, resulting in pi on 2 plus half sine pi minus negative pi on 2 plus half sine negative pi. Notice each term has a factor of a half, meaning we can remove half against the 2, resulting in 1, which is then redundant. By application of the negative, we can simplify even further. Collecting like terms and finding the exact value of these trigonometric constants results in 2 pi, which rearranges to our final form, pi r squared times 2 pi r, the volume of a torus. We have conclusively found the volume of a torus, equal to pi r squared times 2 pi r, proved correct with integral calculus. This problem is a great example that shows the depth of mathematics. To find the volume of a torus, sometimes we find a solution, such as how we did with geometry, that feels correct, but isn't really backed by the certainty of mathematical proof. There is usually more than one way to tackle a problem, so that we can be certain of our solution. In this case, it was through the use of some calculus which provided a more definitive answer. Each individual solution can be correct, but only contributes differently to a holistic understanding, showing us that maths is collaborative. It can be shared, built, and verified by many interpretations.